Good day everyone, it's nice to see you again. Today we'll continue our discussion on Diastereomerism. If you remember, in our last lecture we have already covered enantiomers. Enantiomers are compounds that have one stereogenic center and their mirror images to one another. The mirror image cannot be superimposed in case of enantiomers. Today we'll be discussing about diastereomers. Diastereomers are compounds that have at least more than one chiral center, and they are not mirror images to one another. So if you just look at this model, this carbon right here, this carbon has 1, 2, 3, and this whole thing is the fourth group. So this carbon center is a chiral center, because it has 4 different groups on it. Group 1, Group 2, Group 3, and this whole thing is Group 4. And if you also look at this one, it has Group 1, another group, and it has the whole of this. So both carbons are chiral centers. That means these compounds can exist as several diastereomers where the positions are staggered or switched to one another. So this compound, as a diastereomeric compound, because it has 2 chiral centers, it would exist as 4 different isomers. The maximum number of possible stereoisomers, when you have a chiral center n, for example, in this case, 2 of these are the chiral centers, you have to the power of 2, 4 different diastereomers are possible. So the maximum number of stereoisomers that are possible from one diastereomeric combination is to the power of n. So by going to the board, for example, if you just look at this Pimeotoxin C, it's a natural product, it's highly toxic, it comes from a frog's skin isolated in a very minute amount. It could cause paralysis. This particular diastereomer, meaning that the configuration at each chiral center, this is one chiral center, this is another chiral center, this is another chiral center, this is another chiral center. So there are 4 chiral centers for Pimeotoxin C. So based on these 4 chiral centers, you could write possibly 16 diastereomeric compounds or combinations. For example, I have drawn here 1, 2, 3 possibilities, but you could go to up to 16 of them. The reason is, if you have R, for example, this configuration, remember to review your assignment of R and S, because we have already covered how to assign R and S. So based on that rule, this carbon is R. I want you to check this on a paper. This is S, this is R, this is S. So if we were to assign this compound, this diastereomer for this one, they are not mirror images now. So this would be, obviously, I can easily assign that into S by just looking at that, because the R is coming out of the plane of the board for that methyl group, but the methyl group here is down. Automatically, I can assign also for hydrogen here, if this is S, that should be an R. For this hydrogen, it is the same orientation as this hydrogen. Everything is the same, therefore it remains as R. And for this one, if you just look at this, this is down into the plane of the board, this is out of the plane of the board, therefore this would be an R. So at least the diastereomer pair R, S, R, S. This is one possibility. Here you see it as S, R, R, R. So there are 16 possibilities, like 16 structures that can be drawn as diastereomers. So with this introduction, we'll go past and do actual exercise in identifying diastereomers, and also what are the possibilities of in each compound. For as a review, a diastereomer is a compound that has at least 2 chiral centers, even more, but if you just look at this is a chiral center. From our definition of enantiomers, a chiral center is a carbon which has 4 different groups attached to it. You have 1, 2, 3, and the whole thing is 4th group. On this carbon, if you just look at this carbon, you have the green, purple, and the white. This is different groups, 3 of them, and the 4th would be this whole thing. This has 4 different groups. So both qualify as 2 chiral centers. In this model, both carbons qualify as chiral centers. Therefore, this particular diastereomer have another 3 more that can be drawn, because 2 to the power of 2 chiral centers is 4. So with this, we'll continue in the next section to see different examples of diastereomeric compounds. Okay, let's continue our discussion on diastereomers. In this section, we'll also introduce Meso compounds. I have here a cyclopentane, a di-substituted cyclopentane. This is a dimethyl cyclopentane, dimethyl because you have 1 CH3 here, 1 CH3 here. These are 4 different compounds as you see them, but once we identify each one of them as enantiomeric or diastereomeric pair, we'll see how many possible compounds would get. So if you just look at this compound, you would have the methyl group on the out of the plane of the board. Here the methyl group is down into the board. So let's go back and do our RNA's assignment for this compound. This compound, the priority would be if these are the chiral centers, by the way. You should know this is a chiral center, that's a chiral center, that's a chiral center, that's a chiral center. Because those carbons are substituted by 4 different groups. So in terms of assigning a priority for this, the priority for this carbon would be this group would have a CH2, CH3, CH, so it is a dense group. That means priority 1 would be this one group for this one, and the priority second would be 2, because that is a carbon containing 2 hydrogens, but here it is a carbon which contains 3 hydrogens, but this one has another carbon. So the priority would be 1 carbon. This carbon has 1 carbon here, 1 carbon. So it has 2 carbons in 1 hydrogen. Therefore, it is more prior than this one, because this one is only 2 hydrogens. The last one the third one would be the methyl group itself, but here, luckily, our hydrogen is at the back of the plane. That means it's down here. So we don't have to rotate anything. We leave everything on the plane of the board, so we can just go from 1 to 2. That is counterclockwise. Therefore, this would be an S, because we are going from 1 to 2 in a counterclockwise direction. Now, I will just remove this to assign for that carbon now, meaning that this carbon is the stereogenic center I want to assign it for. Therefore, the first priority would be this whole group would be one group, so this is priority 1, and then second would be this is 2. We are considering this carbon, remember, this is 3. Now the hydrogen is out of the plane of the board, so you need to rotate this thing. So this is out of the plane of the board. So this is a kind of harder for you to just by mentally rotate it so that the hydrogen would go into the plane of the board. So if you want to turn this, one trick I want to do and show you a shortest way is by switching hydrogen to the metal group here. Already the hydrogen would go to back. So this is a trick. This is not actually what happened. So I would redraw this where I have the hydrogen back onto the down to the plane of the board, and metal group now switched to out. That's priority number 3, and leaves everything as such. So here I have this hydrogen is down here, and now remember, now I have this is not the structure. I have just to switch this to this to make it easier for me to mentally rotate this. So it is the same as doing this. So if you switch, remember that you have switched it. So this is 3, this is priority number 1, this is priority number 2. So we are going from here to here, that is clockwise. This tells me it is an R here, but remember I have switched this, so this is not actually what happened. Therefore, if this was R, this would be an S. Okay? So this is a trick we use to just do the R and S assignment. Now, when it comes to this one, now you have the metal group up, the metal group is up here. So you don't have to do anything, it should be an S, right? And for hydrogen up and metal down, this is S, but metal is up here, therefore this is an R, right? This is an S, this is an S, this is an S, this is an R, and now let's see here. So when metal group is up, it is an S, but metal group here in this molecule is R, because it's down. Here it is metal group is up, that means it is up here as well, it is an R. How about here? So when metal group is down, metal group is down here, metal group down is an R, and metal group is down here, also here, that is an S. So we have assigned for all 4 of them. Now the SR is assigned. So let's find out what is the stereochemical relationship between each one of these. So as I said, since we have 2 chiral centers, we could write up to a maximum of 4 different compounds. But the point is now, are they all of them unique 4 compounds? You have to be careful. There are some group of compounds that qualify as meso compounds. They would not be unique when you have a meso compound. So this SS and this RR are mirror images. So the relationship between this and this compound are enantiomeric. So let me put them 1, 2, 3, 4. So 1 and 3 are mirror images to one another, right? This is S, that's R. This is S, that's R. Therefore, 1 and 3 are enantiomers. Enantiomers. How about 2 and 4? But any of the relationship between 1 and 2 is diastereomeric. For example, 1 and 2 are diastereomeric. They are not mirror images. They are SS and SR. So, for example, 1 and 2 are diastereomeric. Diastereomers. How about 2 and 3? This is S and R. This is R and R. So 2 and 3 are also diastereomers. They are not mirror images, but they have chiral centers, more than one chiral centers. How about 2 and 4? 2 and 4. Let's see. S, R, R, S. Since this compound, be careful now, this compound, if you just rotate it like this, it becomes up here, and the R would be up as well. So they are the same compounds. So if you flip the whole compound, the whole thing, this and this are the same. 2 and 4 are same. Same compound. No stereoisomerism between the two. The reason being, a compound that has a plane of symmetry, meaning that if you have a compound like this, where this chiral center is S, and the metal is metal here, and the chiral center is mirror image to that one, within itself, this compound is reflected to this, everything is reflected within the compound. This compound is a meso compound. This is also a plane of symmetry. R is reflected to S as a mirror image. The metal is reflected to that. This and is reflected to this. Therefore, in this such compounds where there is a plane of symmetry within a molecule and the chiral center is exactly reflected within the molecule, that compound is a meso compound. So 2,4 is the same compound, it's just one compound. They're called, that compound is a meso compound. So a meso compound is a compound where you have stereogenic centers that are reflected one over the other through a plane of symmetry within a molecule, and everything is reflected. So those are meso compounds. So 2 and 4 are not different compounds. They are the same compound, because you can just flip this and end up both up. So there will be, if you just flip the whole thing, it will be the metal group, and the metal group will be up also onto the plane of the board. So 2 and 4 are same. So we have how many unique compounds? We have only 1, 2, 3 unique compounds. 3 unique compounds. That's why in the definition of diastereomeric compound, if you have 2 chiral centers, you would have a maximum or possible of 4 different compounds. But when you have a meso compound, when you have a plane of symmetry that reflects exactly that compound through a plane, that would be the same compound. 2 and 4 are same compound. Such things happen when you have a plane of symmetry. And this compound is a meso compound, or this is a meso compound. They are the same. So the stereochemical relationship between 1 and 3 are mirror images, enantiomers, or mirror images. So there are 2 different compounds. 1, 2 are diastereomers. There is no mirror image to one to the other. Therefore, they are not mirror images, but they are diastereomers. So we have only 3 unique compounds. Let's see another meso compound here on the board. This compound also, let's just examine what we have. So is plane of symmetry possible? Let's just look at this. So if you have hydrogen here, and that's hydrogen. That is your plane of symmetry or a mirror, hydrogen is exactly reflected at this hydrogen. Bromine is exactly reflected to this bromine. And metal is exactly reflected to metal group. Therefore, this would qualify as a meso compound. Because let's do the R and S assignment for each carbon, because each carbon has 4 different groups on it. For example, the priority is 1 here, the priority would be 2 here, this group as a whole, and priority would be 3 here, and 4 is this. So like I showed you how to do the trick to take the least priority to the back, you would switch bromine with hydrogen. That's just a fastest trick to see. But remember that you have a switch. So the figure looks like group 2 would be here, Br would be here, hydrogen would be down there, CH3 still remain here. So this is priority 1, priority 2, that's clockwise. That's clockwise direction. It suggests that this is R rotation, but since I have a switch, this would be an S configuration. So remember how to do this mental exercise. So this is an S configuration. Since there is a plane of symmetry, automatically that chiral center, since every group is the same, since it's reflected to that would come as R. Let's just check this. This should come as R because they are mirror images. This is a meso compound. So priority 1, priority 2 still the same, priority 3, priority 4. So if I just switch so that H would be at the back, I will have a redrawing of that. Br would be here, and H would be at the back, replacing bromine. CH3 comes here, still the same place, and this is priority 2. That's the whole other group. So this will tell me 1 is this, 2 is this. This is a counterclockwise S, but since I have switched them artificially, this is an R compound, like I just suggested. So within the molecule, there is an S reflected to R. Everything is reflected. This compound is called a meso compound. This is a meso compound. Okay? As a review, a meso compound is a compound which has more than one chiral center, like this one. S is reflected to R, and each group is reflected by a plane of symmetry, passing through that. This compound qualifies as a meso compound. And review the stereochemical relationship between these 4 structures, actually 3 compounds. This is just the same as that one. So we actually have 3 stereoisomers, and the third one is a meso compound. And 1 and 3 are enantiomers. They are mirror images, 1 and 3. 1 and 2 are not mirror images, but they have chiral centers more than 1. So 1 and 4 are also the same. 2 and 3 is diastereomeric relationship, but 2 and 4 are the same. So how many unique compounds I have? Only 1, 2, 3. Even though what I just told you, when you have a chiral center n number, that is the number of diastereomers. Those are the maximum possible. Otherwise, you could rule out some Meso compound when you have a plane of symmetry. So remember the distinction we have for each of these three compounds and their stereochemical relationship. So I want you to review and also review the assignment we gave for each chiral center. And we'll continue in the next section. So when we continue our discussion on stereoisomeric compounds, we have seen diastereomers, enantiomers, Meso compounds, and on the like. So especially enantiomer, when it comes to enantiomers, because they have the same constitution, the same molecular formula, all of their physical and chemical properties are the same. Between two enantiomers, between R and S, you don't see any chemical and physical differences. The only important activities they have that distinguish them between the two is their optical activity. Their optical activity, meaning that their light interaction is different from one another. It actually is opposite. So the optical activity of an R enantiomer and an S enantiomer are equal and opposite in magnitude. So the way we study their physical property, especially their optical activity, is called polarimetry. So I will briefly describe how the polarimeter works in terms of measuring optical activity of the enantiomers. Here you have a light source, a general light source. That means it is polarized in every direction, in every angle. It's random, as you see it. It has every angle. It travels through every plane. That means it has different orientations in the random way. But in order for us to use it in a polarimeter, we have an instrument part where the light is polarized, meaning that the light that's filtering through the polarizer would have a unique single direction rather than random like this. The reason is just to see what interaction the sample would have. So you shine a light, the light goes through a polarizer. The polarizer would produce a very well-defined light. That means it is a vector in one direction. So when that light passes through a chiral sample, that means an optically active sample, it will deflect to certain degrees. That is the optical activity of that sample. So if that sample is opposite in terms of it is R or S configuration, the same sample with a different optical configuration or would go through that sample would deflect it in a different angle. Equal in magnitude but opposite in direction. As you see, the plane polarized light is deflected in different angle than the other. So that means opposite but the same magnitude. When you have a chiral compound, a mixture of A and B, meaning that a mixture of equal amount of R and equal amount of S mixed, those mixtures are actually called Racemic mixture. So this is a new term you need to learn. When you have an R and its mirror image are mixed in 50-50 proportion, the polarized light passing through that racemic mixture would not change. So that means a racemic or achiral mixture does not have optical activity. The optical activity is 0. So optical activity is measured in degrees. That means how much it will deflect. So as a review, you have a light source. A random light source would be polarized, and this is a plane polarized light. We call this plane polarized light. When you produce a plane polarized light, that is a well-defined angle. That means a vertical angle. It could be horizontal, but a well-defined angle. When it interacts with a chiral sample, a chiral compound, it either deflects in the negative direction or in the positive direction. So it doesn't really matter how much. The only thing is how much it will deflect. But if there are chiral compounds A and B, meaning that for the same compound, if you have an R configuration, S configuration, S or R, it doesn't really matter. It will deflect the plane polarized light either in the negative direction or to a positive direction. But remember, a racemic mixture is a mixture of two enantiomers in 50-50% proportion. So it's a mixture of an R 50% and S 50%. The plane polarized light passing through a racemic mixture or an achiral compound would a chiral mixture would give you nothing change in terms of polar optical activity. So the deflection would be 0. So there is a general term for negatively deflected plane polarized light and for positively deflected plane polarized light. If the plane polarized light is turning into positive direction, it means if it is clockwise, we give it a plus value. So the degree that comes, for example, is plus 30 degrees. That kind of compound is called a D compound or D isomer. It is called Dextrorotatory. But if the plane polarized light is deflected to the left direction, the value would be a negative value. For example, if this is plus 30 degrees clockwise, that's D plus 30, and L is a minus 30 for the other isomer. So D and L are actually the actual absolute way of assigning whether a compound is chiral or achiral. R and S are assigned by just where they are in space. But this D and L measurement comes actually from optical activity, actual measurement of the property of that compound. So clockwise is a D, Dextrorotatory, and counterclockwise, Levorotatory. That means the plane polarized light would be deflected differently or in opposite direction. And the values are measured in degrees. So the optical activity is measured in theta in degrees. So this is overall is called polarimetry. That's how we measure the optical activity of any chiral compound. So optical activity is a property of chiral compounds. If a compound is achiral, if it doesn't have any stereogenic center, or it is not, it's a meso compound, for example. A meso compound does not deflect a plane polarized light. So a meso compound would have a 0 deflection. That means the plane polarized light would not rotate. So this is a term you should be familiar with when you see optically active compounds, because the only difference between two enantiomers, they are physically the same, chemically the same. The only way we differentiate them or we detect them is by their optical activity using a polarimetry. This is an instrument using a light that is plane polarized and shining through the sample. The sample would give you either a positive deflection or a negative deflection. So this is, in a nutshell, this is how you would be measuring optical activity of a sample or a chiral compound. Okay, at the conclusion of our optical activity section and the stereoisomerism, there are two things I want you to know in terms of how we measure optical activity. There is one which is called specific rotation, Remember, I have told you that the plane polarized light would be rotating at a certain angle, and that is the magnitude of what we measure. That's called specific rotation. So alpha is the specific rotation when it is considers the concentration of your sample. So the concentration of your sample is grams per ml. This is the length of the cell to which the sample is put in. Usually it is 10 centimeter, or it will be given. That's just the cuvette or the sample cell that you're measuring in. But in most cases, the specific rotation can be a plus or a minus. As I told you, it could be deflecting it to negative or positive. So for example, if you have a sample where the observed rotation is, say, 18 plus degrees, that's just an example, and you measured it in a 1 decimeter sample, which is 1 centimeter, 1 decimeter is 10 centimeter, and let's say you have your concentration is 1 grams per cc or 1 gram per ml per cc, centimeter cubic. So the specific rotation for this sample would be 1.8 degrees. That's just per gram per cc. So that's the specific rotation. This is the total observed rotation. That means when you have your sample at 1 gram per centimeter cubic or cc, that is the whole thing. But you want to know per gram what specific rotation you'd get. So 18 degrees was for the whole of the sample, but the specific rotation, when you consider its concentration, it's called a specific rotation. So the total rotation is different from specific rotation in that the specific rotation takes into account of the concentration. So this is the concentration of your sample. This is the length of the cell. This is what you measure. So alpha observed is a measured value. That's measured. And L is the length of the cell. That's what you measure your sample in. Usually it is 1 decimeter, which is 10 centimeter. Grams per ml is concentration of your sample. By that you can just calculate what is the specific rotation for that sample. So when you measure the specific rotation, if the observed rotation is 0, it all immediately tells you that the sample is achiral or it doesn't have any optical activity. So any optically active compound should give you either a plus or a minus. This could be plus, minus, depending upon which direction the rotation happens. The other value we also into when we discuss stereochemistry is enantiomeric excess. Enantiomeric excess means that usually is a 50-50 mixture of R and S is called Racemic mixture. But you don't always get a 50-50 mixture or one over the other. So you want to measure what is the enantiomeric excess, meaning that what is the pure enantiomer that is over the other. So if somebody gives you a 70% enantiomeric excess sample, it means that the difference between one enantiomer over the other is 70%. That means if you have this difference, that means one enantiomer A, let's say enantiomer A is 100%, minus the enantiomer of the other is 30%, the enantiomeric excess would be 30%. So that's what it means when we say enantiomeric excess. So enantiomeric excess is equal to, let's say enantiomer A, let's say if we take that as 100%, A, the other enantiomer or the mirror image is, let's say, 30%. This would give us a 70% EE, enantiomeric excess. So we can also just use a percentage, or the other way of determining enantiomeric excess using the alpha value also is possible. For example, you could measure the alpha of the mixture that can be measured, and if you divide it by the alpha of the pure enantiomer, such as this, if you have a mixture, for example, give you certain amount over the alpha of a pure enantiomer times 100 would give you also a percentage of the enantiomeric excess. So enantiomeric excess can be just using the specific rotation, can be determined by just the ratio of the pure alpha and the mixture times 100, or if you are just given the enantiomeric excess, that means 100% of A minus 30% of the other enantiomer will give you 70%. Sometimes you could be asked, for example, what is the total amount of the total percentage of A and the total percentage of B. That is the total percentage in terms of enantiomeric excess. That means 70% enantiomeric excess means 30% is a racemic. Okay? So the enantiomer percentage of A, the total, I am not saying the excess, the total amount of A would be, in this case, 85% A and 15% B, the other enantiomer. The way I did it is, if you have a 70% enantiomeric excess means the 30% is as a mixture of equal mixture of A and B. So the total amount in the sample of A would be then 1 from the excess, which is 70, and half of this is 15. 70 plus 15 is 85, and 15 is the percentage of B. It might be a little confusing, but this is how you do it. The 70% enantiomeric excess mean, that is how much A is over B. And if a question comes where you'd be asked, in the total sample, what is the percentage of A? This is how you do it. Okay, if 70% of enantiomeric excess means that the rest 70% is a mixture. The rest of it. And that mixture is actually composed of 15% of A and 15% of B. So that means 15% A and 15% B. That is the racemic part of it. 70 is the enantiomeric excess of A over B. That means how much high it is enriched it is with A, but the rest of it is a mixture, which is 30%, racemic mixture. Out of that 30%, if you want to know each one of them how much they are in a sample, therefore, just a 50% mixture of that means 15-15. So add 15% to A, which is that excess, 85% of A and 85% of B. This is a total percentage of A and a total percentage of B. So that's how we usually do the calculation. So if you just subtract these two, you'd get the enantiomeric excess. 85% of A minus 15% of B will give you the enantiomeric excess. So this is how you calculate enantiomeric excess. 85% of A minus 15% of B is the enantiomeric excess. With this, we will conclude the section on stereochemistry. I will be solving several problems from stereochemistry in the next video. Please review those problems of the stereochemistry section. Thank you.